Let's talk about Romberg's method. This is a new idea doing the integration. We are trying to get a good approximate value of an integral. So, what is the idea of Romberg? When we applied trapezoidal, our very first idea, our most simple idea, but we saw it's not a bad one, it's quite a good one. Okay, here in that plot, we see here with these values, we get that approximate value for the integral. And this approximate value is not very good. Why? Because the red line and the blue curve, there is a large difference here, and so the approximate value will not be the best one. But if we subdivide here, these were our original evaluation points, and now we subdivide, so half each interval, and then the red curve and the blue curve are much closer, and so the integral value here below the red curve is much better. Here it's not very good, still not very good, so the approximate integral value coming from the trapezoidal rule will be better than the first one, but will not be perfect. Okay, then last time we had that structure, and then again we subdivided, and now the difference between the red curve and the blue curve is quite small, and so now the integral value from the trapezoidal rule will be much better than it was before. But again, this integral value will not be perfect. So what is the idea of Romberg? If you use the function e to the power of 3 times of sine x, this is the function, and you integrate from 0 to 1. And if you use two parts, then you have h is a half, and the trapezoidal rule, applying this rule, will give you that integral value. So this is that point 5.4766, and where does it come from? It comes from, here is the interval 0, 1. This is the function f, and then using h is a half, so we evaluate that function here, here, and here, and then we do the trapezoidal value, which is this area, and calculating this area, this is 5.4776, and then this is the point. Okay, and then if we have this h, that means here again is our interval 0, 1, and again here is our function. And then if we use h to be a quarter, then we evaluate the function at these points, and then we integrate that, and we get that area, and then this area is 5.1961. Okay, I hope you understand the principle. And here again, use an h which is refined, half 0.25, and you get 0.125, and then you get the integral value coming from the trapezoidal rule to be 5.1280. And if you subdivide into 16 parts, then you will get the approximate value 5.1111, which is that value. Okay, so I hope you understand what's going on here. And if you see that, then there's a very natural idea. The very natural idea is, okay, maybe this is the correct value, this one. Because in this example, if h is chosen smaller and smaller, the values will get smaller and smaller. But there will be a tendency, and this is that. So the idea is, let's interpolate these 4 points and then evaluate at position 0, and the hope is maybe we get a better value and better approximate value for the integration value of e to the power of 3 times sine x and integrate it on the interval 0, 1. And this is that idea. Okay, and we know from the trapezoidal rule that in fact, if you refine h, if h is chosen smaller and smaller, then the trapezoidal sum for the corresponding h converges to the correct integral value. And so let's do. We use that example and then we run the following code. Here is our integrand, exponential of 3 times sine x. Then we use the quad command. This will produce an approximate value, but accuracy is, if I remember correctly, is 10 to the power of minus 8 at least. So quad will produce an value, an integral value, which is very close to the correct one, but it's not really correct, okay? Then we apply the trapezoidal rule for our f function. We integrate each time on the interval 1, 0, but we split the interval for k is 1. We split into only one interval, so we integrate from 0 to 1 and only evaluate at these 2 points. And then if k is 2, then we evaluate at the midpoint also. If k is 3, then we evaluate also at these points, and if k is 4, then we evaluate at these points. And so we get 4 integral values, and now we interpolate these values, the h and the I. What is that? Here are the h values, and that are the I values, okay? And now we find the polynomial of degree 3, interpolating these 4 points, not the points here, no, not these points, but the points above in the corresponding diagram. And then we evaluate that polynomial at position 0. That will give us the polynomial, the absolute value of the polynomial, okay? And this, we hope, we think that this value might be better than all the values before were. And now we see, if we take the difference between our approximate trapezoidal value and the correct value, the correct integral value, then we see for trapezoidal with h is 1, we get this difference. So our trapezoidal value was not very good, was very bad. Now the difference to the correct value gets smaller and smaller and smaller. And if we use our idea above, then we get an error, a difference, which is approximately a tenth. And this is quite surprising because the basis of our improved value are the values which were not very brilliant, but by using them we were able, at least in that example, to get a better accuracy. Okay, and I think this was the starting point of Romberg. I think he did exactly that, what I showed you, and then he worked a long time on this topic, and then he found out something which was quite brilliant, and I will show you in the next videos. But to be honest, in the end, the idea of Romberg's looks like quite different, completely different to that idea. But in the very end, in our chapter Romberg, we will come back and then I will show you the link. So in the next video, everything looks completely different. But in the last video about Romberg, I will show you, yes, this is more or less the idea of Romberg, but Romberg even refined that idea. Okay, this was our first video, and I hope that I was able to motivate the Romberg method.